Hello everyone, this is Bhumi Shah, Assistant Professor, LG Institute of Pharmacy, Pharmaceutical Chemistry Department. Today we are going to discuss in detail about macrolide antibiotics. Today we'll discuss their history, chemistry, their properties, mechanism of action, spectrum of activity, therapeutic uses, and side effects. Macrolide antibiotic, first macrolide antibiotic, that is erythromycin, and that is discovered in 1950s from a soil bacterium called Erythromyces streptomyces erythris. From a soil bacterium called Streptomyces erythris. Then after in late 1970s and 1980s, synthetic derivatives of macrolide antibiotics have discovered like clarithromycin, azithromycin, and all. Basically, structure of macrolide antibiotic, they possess three main groups. First, lactone ring, large lactone ring. Second, ketonic and hydroxyl functional group. And third, sugar molecules. That sugar molecule is glycosidically linked with the lactone molecules. Due to this lactone, a large lactone ring, this group of antibiotics are known as macrolides. Right? See, in the structure I have mentioned which is a lactone part, which is a sugar part. Sugar part that is attached with a lactone molecules by a glycosidic linkage. Due to this lactone ring, a large lactone ring that may be a 12 carbon, 13, 14, 15 and 16 carbon. And so according to that numbers of carbon, the macrolide antibiotics, they are classified into five groups: 12 member ring macrolide, 13 member ring macrolide, 14, 15 and 16 member ring macrolides. Most of the macrolides, they belongs to 14 or 16 member ring macrolides. Then characteristics of this, general characteristics of this macrolide antibiotics. See, in this structure I have circled that is amino group, dimethyl amino group that is present over this sugar molecule that imparts basic characteristics to the antibiotics. Due to this property, they can form salt at pK value 6 to 8. Then this antibiotics, they are water insoluble and they are stable at or below room temperature, but they are unstable at higher temperature as well as in presence of acid and base. So there is a need to develop a derivative which are water soluble or which have stability against acid or base or at a higher temperature. So chemical modification is then applied to develop water soluble derivative or a derivative which are stable against acid, base or at higher temperature. So salts can be prepared from glucohaptonic acid or from lactobionic acids. They are water soluble. If the derivatives are water soluble, then we can use that derivatives in a parenteral preparation. Right? The next, salts like erythromycin acetate make them more acid stable. And so, if they are acid stable, then it promotes oral absorption, high oral absorption. Right? So, these are the two chemical modifications proposed to improve their stability as well as their solubility. Then we'll discuss structure of erythromycin, clarithromycin, and azithromycin in detail. This is structure of erythromycin. There I have highlighted three parts: lactone ring, clarinose moiety, and amino sugar. Lactone erythromycin possesses 14-membered lactone ring, and that is known as erythronolide, while amino sugar, which is attached at fifth position to the lactone ring, and this amino sugars, they are known as desosamine. Another sugar molecule, that is clarinose, that is attached at C3 position with the glycosidic linkage to the lactone part. Now erythromycin, this is the structure of erythromycin A. Erythromycin possesses three varieties: erythromycin A, erythromycin B, and erythromycin C. They possess a little bit difference in their structure. See, here I have shown you a structure of A. In case of erythromycin A, we have hydroxyl group present at 12 position. While in case of erythromycin B, instead of hydroxyl group, we have H, hydrogen, at 12 position. While in case of erythromycin C, we have modification in a clarinose moiety, means in erythromycin C, we have H in place of OCH3 group, which is shown in a erythromycin A structure, right? So three modification. In case of erythromycin A, we have hydroxyl group at 12 position. In case of erythromycin B, we have H in place of hydroxyl group at 12 position, while erythromycin C that have H in place of OCH3 at clarinose moiety. Why we have to discuss these three varieties, erythromycin A, B, and C? Because a clinically grade erythromycin, they contains 90% of erythromycin A, while rest of 10% they have mixture of majority proportion of B with a minute quantity of C. Then next we have two semi-synthetic derivatives to be discussed, that is clarithromycin and azithromycin. They are semi-synthetic, means little bit modification in erythromycin structure, right? Let us first discuss clarithromycin. How they differ from erythromycin? Only one difference. In case of erythromycin, we have hydroxyl group at 6th position. H of hydroxyl group is replaced by CH3 group. So OH group converts into OCH3. Hydroxyl group converts into ether group, right? So ultimately clarithromycin is 6-methyl ether of erythromycin. Due to this modification, it possesses great acid stability than erythromycin. The next structure is azithromycin. Here we have two modifications compared to erythromycin structure. As in case of erythromycin, we have 14-membered lactone ring, which is known as erythronolite. While in case of azithromycin, we have 15-membered ring structure, and which is known as azalites, which is known as azalite. Another modification. In case of erythromycin, we have ketone functional group at 9 position, while here in azithromycin, we have absence of ketone functional group. So two modification. First, a lactone ring instead of 14, here we have 15. Second, absence of ketone functional group at 9 position. Again, due to again due to this two modification, that increases stability to acid catalyzed degradation, means they are not degraded in presence of acid. Then mechanism of action, most important part, how does antibiotic act? One kind of mechanism we can say, they inhibit bacterial protein synthesis. Then how? So they bind themselves to 50S ribosomal subunit and suppress RNA dependent protein synthesis. See here in figure I have mentioned a macrolide molecule comes and binds with 50S subunits, and so that it prevents elongation of polypeptide chain. So ultimately hindrance in a protein synthesis, right? So this is mechanism of action includes inhibition of protein synthesis by reversibly binds to the 50S subunits of ribosome and interferes with translocation of mRNA. The next, spectrum of activity. This group of antibiotic mostly shows bacteriostatic action, but for a susceptible organism, they show bactericidal action, but again, that is at a higher dose. Let me revise you what is bacteriostatic and what is bactericidal. Bacteriostatic means they prevent growth of bacteria, while bactericidal means they kills the bacteria, right? So they possess bactericidal activity only against some organism, but again at a higher concentration. Now we have to discuss the spectrum of activity against erythromycin, clarithromycin, and azithromycin. Against gram-positive aerobes, erythromycin and clarithromycin display best activity, while against gram-negative aerobes, this azithromycin shows better activity. Then adverse effect. At its therapeutic dose, this macrolide antibiotics, they shows GI discomforts, nausea, vomiting, diarrhea, and sometimes to some objects they show mild allergic reaction. While in a toxic dose, means at a higher concentration, they produces liver toxicity, jaundice, and reversible hearing loss. Most important section, how where these macrolides are useful. They are useful for upper and lower respiratory tract infections. That includes pharyngitis, tonsillitis, cough, pneumonia, etc. Now, this is the reason why this azithromycin have been tried for COVID-19, right? Because azithromycin have their effects in pneumonia, tonsillitis, and all. So this azithromycin is now in a clinical trials against COVID-19. Thank you. Hope you enjoy this lecture. If you have any query, you can comment below the lecture and you can subscribe for more videos. You can subscribe our YouTube channel Pharma Ignite. Thank you.